Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 1 on dilations. So we now enter a distinctly different portion of this course. Everything basically up to now has been concentrating on figures that are congruent to one another. Same shape, same size. But we're now going to get away from that and it's all going to be based on what are known as dilations. So let's jump right into it and kind of talk about that. And let me reiterate, so far we've concentrated on rigid motions that preserve both distances and angles, right? So it preserves the shape and the size of a figure. We will now move on to another type of transformation known as a dilation that preserves the shape of an object, but not its size. Dilations are very important in the real world, especially when you take, let's say, an image and you stretch it to make it larger or compress it to make it smaller. You're going to be changing the size of that image, but you ultimately don't want to change the shape of it because you still want to make it look like a house or a tree or a person's face or whatever. So let's take a look at exercise number 1. Triangle ABC is shown plotted with vertices at A, 3, 4, B, 4, -2, and C, -2, -1. Given the following transformation rule, F takes x, y and maps it to 2x, 2y, map triangle ABC using the rule. Label the image triangle A', B', C', show the mapping below. All right, well this is an exceptionally easy mapping, obviously, right? So let's do the mapping and then we'll do the plotting, okay? So all I want to do, right, is I want to take A, which is at, not 2, which is at 3, 4, and this mapping rule just tells me to multiply both the x and the y coordinates by 2. So A' will be at 6, 8. B, which is at 4, -2, will get mapped to B', multiply both of those by 2, and we get 8, -4. And finally, C, which is at -2, -1, will get mapped to C' at -4, -2. Awesome, right? Let's take a look and see what it looks like, right? We've got A' at 6, 8. We've got B' at 8, -4, and we've got C' at -4, -2. Maybe I'll use my ruler now. Wait, that's not -4, -2, that's -4, -3. Let's try that again, -4, -2. So let's connect our vertices. I'll get them all labeled in just a moment. And let's do our final one. Okay, so we've got our A', B', C', and there's our new figure. Obviously, ABC, triangle ABC, is not congruent to A', B', C', but they are the same shape. And we'll talk about what it means for two figures to have the same shape, but a different size as this unit goes on. Let's get into it and formally define what dilations are. Dilation, the technical definition. A dilation will enlarge or shrink a geometric object by some scale factor, right? And we can think about in that last problem, the scale factor was 2. In other words, we were doubling the lengths of all the sides. I hesitate to say that we were doubling the size of a figure because what does that exactly mean? Does it mean we're doubling the lengths of the sides, we're doubling the area, we're doubling, what does that mean? But really, we were scaling every side length so that it was twice as long as the original sides. But dilations have a very technical definition that's critical to know. So let's take a look at what that technical definition is. A dilation, D, with a center at point C and a scale factor of K, maps a point A to image point A' such that if A is the center of dilation, i.e. if it's just point C, then the dilation of point A is just point A. In other words, dilations do not move the center point. This is similar to when we reflect a point that is on the line of reflection, it doesn't go anywhere. Now, the more important one is number 2. If A is not the center of dilation, then the dilation of A equals A', where A prime is located on ray CA such that CA prime, right, which is the distance from C to A prime, is equal to K, that scaling factor, times CA. All right, so let me help you visualize that. That sounds awfully complicated, but it really isn't. Here's this deal, right? Let's say I've got point C and I've got point A, right? And I want to dilate point A with respect to a center point C with some scale factor K. So the first idea is, well, where will A prime be located? Well, A prime is going to be located somewhere along ray CA, okay? Well, where is it going to be located along ray CA? Well, it's going to be located somewhere such that the distance from C to A prime is K times the distance from C to A. Now, where that lands depends on whether K is greater than 1, in which case we go farther away, or less than 1, in which case A prime moves closer to C, right? So if I've got the distance CA, then CA prime, right, in this case, K would be greater than 1, CA prime, right, will be K times CA, all right? That's all it is. We are simply moving a point either farther away or closer to the center of dilation based on some scaling factor. In that first problem, that value of K was equal to 2. And that's not an unusual value of K. So let's do a little, just sort of like real kind of rough dilation here. Exercise number 2. Given points C, E, and F below, use a ruler to plot the image of each of the following. A ruler, not just a straight edge, but a ruler. Letter A dilation of E with a center at C and a scale factor of K equals 2. Label as E prime. All right, so again, I know that some geometry teachers would say never use a ruler in geometry. I think that's really weird. That's like never using a thermometer in chemistry or a scale in physics, but whatever. All right, now the idea here is if I want to locate where E prime is, the first thing I'm going to do is I'm going to literally take my straight edge and I'm going to draw a ray through C and E prime and E, okay? Now E prime lies somewhere along that ray. Somewhere along that ray, E prime lies. Where should it lie? Well, it should lie twice the distance away from C that E is. That's what K equals 2 means. Well, right now, at least based on my ruler, this distance is 4.5 centimeters, which means that since CE is 4.5, right, CE prime has to be 2 times 4.5, which is 9, which means C prime must lie right there. Not C prime, E prime. I apologize. All right? So E prime is getting twice as far from C as E was. All right. What I'd like you to do is see if you can figure out where F prime must be. Pause the video now. Okay. Well, just like before, what I know based on the definition of a dilation is that F prime must lie somewhere along that ray. F prime has to lie along the ray CF. Okay, but now we want the distance from C to F prime to be 1/2 the distance from C to F. So what is the distance from C to F? Looks like it's, apparently I can't write at all. Right, this looks like it's 6 centimeters. All right, so because CF is 6 centimeters, we want CF prime to be 1/2 of 6, which is 3 centimeters, and that means it's got to be located right there. I don't know why. My pen is really not happy with me right now. It's got to be located right there. I think it's the proximity of the ruler. So F prime has got to be right there. All right. Now, in general, we won't be doing dilations with rulers, okay? But this really hammers home what's going on here, right? When we dilate points with a given center and a given scale factor, right, the image point will lie on a ray that starts at the center, goes through the point that I'm trying to dilate and continues to go on, because rays go on forever. And then where is it located along that ray? Well, first I need to know the distance, right, that between my center point and my pre-image point, and then I simply multiply that distance by whatever my scale factor is to find the new distance from the center point to the image point. All right, that's all a dilation is. So let's keep going. Now, let's talk about dilating lines and line segments, right? Because we were just in that case dilating points. We now want to look at what happens when you dilate all of the points that lie along a line or a line segment. We start with the case where the center of dilation is located on the line that we're trying to dilate, all right? Now, this is kind of a special case, but it's an important one. So let's take a look at that in exercise number 3. Given point C that lies on line AB shown below, do the following. Letter A, using a compass and straightedge, dilate both A and B using C as the center and a scale factor equal to 2. All right, now this is kind of cool, right? Because I can now figure out where the image of point A should lie under this dilation by just ensuring, right, that its image lies twice as far away from C as what A did. Now, the way that I can do that very easily is, well, that's the distance that that's the distance that A is away from C. If I want A to be twice as far away, I then can just move my compass over here, and now A prime is twice as far away, right? You go ahead and pause the video now and figure out where B prime lies. All right, let's take a look. So let me flip my compass around a little bit. We're going to do the same thing. I just have to widen it a bit. Oh, right on the money. There's B. Bring it over here. There's B prime. And now B prime lies twice as far away. All right. Now this brings us to something that is an interesting point, even though it doesn't seem all that relevant. What can you say about the lines AB and A prime B prime? Well, what can you say about those two lines? Pause the video now and see what you can say. Now keep in mind, we're talking about lines here, not line segments, lines, right? And what you can say for certain is they are the same line. They're the same line. Right? I mean, the same line passes through A and B as passes through A prime, B prime. And that is always the case when you dilate an entire line using a center point that lies on that line. And it kind of makes sense. I mean, if I have a line that goes on forever in two directions, and I got some point that lies on the line, and then I stretch that line out or shrink that line down, right? Since the lines are infinitely long, it just remains the same line. It doesn't rotate or anything like that. It just, right? It's the same line. That's not the most interesting part of dilations. Of course, what's more interesting is when we dilate, right, a line segment using a center that's not on the line containing the segment, right? It's far more interesting when the center of dilation isn't on the line that we're dilating. In this case, there's two important properties that occur with the image segment. So now we're going to dilate a segment and not a full line. So let's take a look in exercise number 4. Given AB shown below, along with point C, do the following. Letter A. Using a compass and straightedge, construct the image of AB after a dilation with a center at C and a scaling factor of k equals 2. Leave all marks, label the image A prime, B prime. Awesome. This is actually very similar to what we did before, except, right, we actually have to draw those rays that our image points are going to end up lying on. So for a moment, I'm just going to move my compass out here, and let's find the image of point A. All right. The way that I'm going to do that is I'm going to take my straight edge, so I'm considering it a straight edge right now, not a ruler, and I'm going to draw a ray that goes through the center of my dilation and just kind of extends a ways. I don't know how far I have to extend it, but it's going to have to be a ways. Now the image of A prime, or sorry, the image of A, i.e. A prime, lies somewhere along that ray. And I want it to be twice as far from C as what A is. So just like what I did in the last problem, what I'm now going to do is I'm going to bring my compass down. I'm going to put its point on, whoops, that didn't work well. Let me move my ruler, get it out of the way. I'm going to put my compass's point down on C, stretch the compass out so that it's got a radius of CA, and then since I only want it to be twice as far, I just move my compass over, keep that to be the same, and I locate point A prime. Awesome. Now what I'd like you to do is pause the video and do the same and locate point B prime and then draw in segment A prime, B prime. Go ahead and do that. All right, let's do it. So we're going to move our straight edge over, rotate it just a little bit. There we go. Thank you. Draw out that ray. Again, how far? I don't really know at this point. Now I bring my compass in. I'm going to maybe go like this and rotate it. I got to figure out that length to be. It's pretty close. I want it exact, but I'm not going to be able to get it exactly. That's unfortunate. That's okay. Hopefully you'll be able to do a better job than I can. And that's B prime. All right. Now that I know where B prime is and where A prime is, I can now draw in segment A prime, B prime. And there we have it. All right, cool. So now we've dilated an entire segment by dilating, granted, the endpoints of that segment. All right, let's take a look at letter B. Measure the lengths of AB, segment AB, and segment A prime, B prime in centimeters. Round to the nearest tenth if needed. All right. Well, why don't you go ahead and measure those two lengths. My length is probably going to be a little bit off on A prime, B prime, just because my arc was a little bit off on point B. Pause the video now and go ahead and measure those two lengths. All right, awesome. Let's take a look. All right, for segment AB, we've got a length of 4 centimeters. And for segment A prime, B prime, we have a length that should be 8 centimeters, but is a little bit off because, as I mentioned, I was a little bit off on that mark. All right, 4 centimeters and 8 centimeters. Now you might say to yourself, well, of course that thing is 8 centimeters long, right? We dilated with a scaling constant of 2. Except keep in mind, what we dilated were the endpoints, right? You know, and then the line segment kind of came along with it. So that pretty much gets down in letter C. What is true about the lengths of the segments? Write an equation relating them, right? Well, what was true about the lengths of the segment was the length of the segment A prime, B prime was equal to twice the length of segment AB. So segment A prime, B prime is twice the length of segment AB. What I really want to emphasize here is that the segment A prime, B prime was equal to that scaling factor times the length of AB. So not only did each endpoint get twice as far from the center point as the pre-image point, but the actual length of the segment that connected to the two also got twice as long. And that's not immediately obvious just because we've moved the two endpoints twice as far away. But there is one other important property, and I need to move that picture back into the frame so that we can really look at it. Letter D. what else appears to be true about the two segments? What appears to be true about A prime B prime versus AB other than the fact that A prime B prime was twice the length of AB? Pause the video now and write down what you observe. Well, it appears that they are parallel, right? That this ends up being parallel to that. In other words, A prime B prime is parallel to AB. These two properties of dilating a line segment are absolutely critical. So let's take a look at them. The fundamental theorem of dilations. Anytime you have anything called the fundamental theorem of blank, it's important. If a line segment AB is dilated using a center point C not on line AB and a scale factor of k, then A prime B prime will be k times AB, and segment A prime B prime will be parallel to segment AB. All right, and this is, I can't emphasize this enough, because the technical definition of dilation is all about dilating points, right? So when I dilate this line segment, I'm dilating every point along it by really, in theory, drawing a ray through every single point and then making every point k times, its distance from C, right? But the result of it, which is really cool, is that as I dilate that segment, right, whether I dilate it smaller or whether I dilate it larger, what's happening is that my image segment is getting scaled at the same amount as the scaling constant, the length of it, and that image segment is staying parallel to the original segment. Really, really critical to get that, okay? Because that is going to form the basis, those two things. The fact that the segment length is k times the original segment length, and the fact that the image segment is parallel to the original segment, those two are going to form the basis of everything else that we do in this unit. Now, of course, keep in mind, this is true as long as the center of dilation doesn't actually lie on the line or line segment that you're dilating. If it does, then we go back to that boring case that we looked at where it's just like, oh, it's the same line. Anyhow, so let's take a look at one last problem. Exercise number 5. In the image below, segment MN is the image of segment KL after a dilation centered at point C. Locate and label point C. Ooh, locate and label point C. I'd like you to pause the video right now and see if you can think about how to locate point C, the center of dilation. Well, keep in mind, right, that M and K, right, M is the image of K, right, those two things lie on a line that also contains the center of dilation. So if I just took my straight edge, let's say, and drew a line through point K and M, right, somewhere along that line, let me actually shift it down a little bit like this. Somewhere along that line, our center of dilation must lie, okay? Because that's just the deal. The center of dilation, the pre-image point, and the image point are all collinear, okay? But that should be true as well for N and L. So if I want to find my center of dilation, I can also draw a line that passes through L and N, and where they intersect must be the center of dilation. All right, you're going to see a picture like this many times throughout this unit, which is essentially, right, something that looks like a triangle with a smaller triangle inside of it. Now let's take a look at letter B. Determine the scaling constant, K. All right. Now this is very important. Whenever we're determining the scaling constant of a dilation, we always want to pay attention to which segment is the image and which segment is the pre-image. MN is the image. This is the image segment. And this is the pre-image segment. All right, and that's amazingly important, right? Because we've got this equation, right, that says that the length of the image segment, MN, must be K times the length of the pre-image segment, KL. All right, so that's always true, right? That was one of those fundamental pieces that we just saw. The length of the image segment is equal to K times the length of the pre-image segment. Well, that means that that K is just going to be the length of the image segment divided by the length of the pre-image, right? The image divided by pre-image. In this case, the image segment has a length of 12 and the pre-image segment has a length of 16, and I can reduce that down to a K value of 3/4. All right. Very critical. We're going to have to calculate the scaling factor a lot throughout this unit because this unit's all about dilations, okay? And always, 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 it will always be an image length divided by its pre-image length. It would be so easy because we're so used to taking a larger number and dividing it by a smaller number. It'd be easy to be like, oh, 16 divided by 12, in which case we would get 4/3 instead of 3/4. But it's always image divided by pre-image. All right, so finally, letter C, explain why MNLK must be a trapezoid. Oh, this is take me back to the last unit, right? Pause the video now and see if you can explain why figure MNLK must be a trapezoid. Well, that's the other piece of our fundamental theorem of dilations, which is that the image segment must be parallel to the pre-image segment. So because MN is the image of KL after a dilation, right, then what we know is that MN is parallel to KL. So MNLK has a pair of parallel sides, right? And the definition of a trapezoid is that it's got at least one pair of parallel sides, so that thing has to be a trapezoid. All right, let's summarize what we just did today. Now, you should have seen dilations back in 8th grade math, and you should have worked with them quite a bit, including much of what we did today. But the technical definition of a dilation is a bit tricky, right? And I really want to emphasize that whole idea that when you're dilating a single point, the idea is I've got a center, I've got the point, right? I draw a ray that starts at the center and goes through the point I'm trying to dilate. I then have that distance from the center to my pre-image point. I multiply that distance by whatever my scaling factor is. Could be greater than 1, in which case the point moves farther away. Could be less than 1, in which case the point moves closer, right? Once I have that new distance, I simply measure the distance off from my center of dilation along that ray, and that's where my image point is, right? Now, that led us, though, to the most important thing in this entire unit, which is the fundamental theorem of dilations, which says when we dilate a line segment with a center point that doesn't lie on the line segment, or on the line that contains the line segment, then two things are true. The length of the image line segment gets scaled by exactly the same as the scaling factor that you use in the overall dilation. And number two, very, very important, the image segment ends up being parallel to the pre-image segment. Those two things then are going to result in a dilation preserving the shape of the pre-image, but not its size. All right, and we'll get into that a lot more, obviously, as we go through this unit. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.